Okay. As I was talking about this counter logic, so uh, you can refer to this entire code and then understand it. It would be easy. The source code is also available here. You can download that zip file and you'll see the source code. But when we included the entire code, when we copy pasted this code to our machine, then it didn't work. The reason being is that there are certain board specific optimizations or inclusions in the code that you must do before it works perfectly. In this project, this website, they would have tested for some other board. So we couldn't use this directly. We searched the internet entirely for this, and I'm actually like, it took like we searched many places for this thing. We watched few videos, YouTube, everything. We searched everywhere to get this thing. But fortunately, to get this HDMI, any basic thing that we can edit, which already works in the Zybo board, we just edit it for our purposes because we don't know the basic thing. So we searched everywhere. Unfortunately, someone has took the same code in the FPGA for fun thing, and then they optimized it for Zybo board, like whatever board that you will be using next. So this is the link. I pasted this link in the slide. So if you see these things, MMCME2 base, these are the things that this person added. So only when you add these things along with this whatever logic that they gave, only then will the code work. So again, some few, so this we didn't know. I think it would have took us many days to figure this out. Fortunately, this code is available. Now, you will be using these two codes. This TS encoder is a submodule. So you will be using these two files and then first test it. You should see this output, like whatever output. You should see the screen to look something like this. After you get that pattern, now next you will be editing these wires. What is the red color? What is the green color? What is the blue color? So this is the logic of color generation. You will understand. You can easily check this out. I'm giving this like this is something which you can build your HDMI logic. So again, it's very easy. This module you'll just connect it to the top module. You'll have one top module in the entire chip. That top module connects the processor. The top module connects the display, everything. That is the module which takes the system clock as input. So in that top module, you'll be assembling everything. It's just like one big thing on which connects all this. So this is regarding the display and keyboard. Again, the challenge that we faced with the keyboard is that the keyboard that we got is the PS2 keyboard, PS2 protocol keyboard, the old one. You cannot program a USB keyboard. There is also a USB, like I told, there is a USB port in the Zybo board, but that is accessible only through when you have a special, I think, like a licensed version. When you have a licensed version, you can download that. There is some name for those module, not it's not modules, but you can download that particular module for which you can through which you can access the USB keyboard. And also the USB protocol would be difficult to program. So which is why you could use this keyboard interface. So the keyboard protocol, PS2 protocol is very simple. The keyboard, if you see, there are 4 wires in the keyboard. I think, yes, there are 4 wires, like wires, it's what the PS2 board. I'll show the picture of PS2. PS2 pin will look something like this. There are six, but you'll be using only four. The four are something like this. One is data port, data wire. The other one is the clock. So the data is received. Both the clock and the data will be from the keyboard itself. So you have to gauge your, or you can say what you have to detect the data based on the clock. So you can study the PHP protocol. We manually studied the pattern, like we pressed one key and then saw the output. There is also this debugging, on-chip debugging thing in Vivado, where when the chip is running, you cannot debug, right? So what happens is that you can write additional code. It's very easy. You'll have uh, additional modules which will monitor your module. That will make the design complex, but you don't have to worry about. But what it is possible is that when you connect the JTAG programming cable to board on your laptop, when the processor is running, this particular module which is added, which is the debug module, will send signals to your computer where you can monitor. It's like, just like simulation, but you'll get real-time data of the system to your computer, of the all the wires and variables to your laptop, where you can monitor like what is happening, right, even if you can't see. So we use that, and then press the key, so what is coming in all the four wires. And we also have to figure out which wire is which one, which wire is the this thing, everything. So based on that, we got that. We studied the things. We studied the how the PS2 protocol works. So I think 10 bits. I think there are 10 clock cycles. 8 bits is the ASCII value, not ASCII value, Unicode value, not even Unicode, byte code. There's some name. So it's not ASCII value. The keyboard, when you press a key, we thought it was ASCII, but it's not ASCII. When you press a key, the byte, the whatever data that you get, it's not ASCII, but it's something, some scan code is, the name is scan code. So you'll be getting scan codes of it. It is also 8 bits, but it's different from ASCII or Unicode. You'll be getting that, and then you have to convert that to ASCII, and then you do all that things. Your primary goal, like I said, the primary goal in data display should be, you have to achieve something like this. You have to achieve this thing, this screen. If you can achieve this, it's simple. And later, maybe you can step by step try to read from memory and then display that. That would be the display part. And keyboard, what you can try is that whenever I press a key, let the LEDs display that. Like when I press A and the scan code of A, the letter A is like 23. It's hexadecimal 23. Then let us just display 23. Two are like the last 4 bits, which should be 3. So if you are able to display that particular scan code in the LEDs, that's what first we tried. We can also try that. Then you will be then you can say that you have hold of, like you are detecting the input. Now, once you detect the input, where to store, I'll be telling you now. But you can also use this PS2 receiver. This is the code. This is a state machine. Again, the PS2 protocol is a state machine, which means that when you press caps lock, that information will be stored not in the keyboard, but that information should be stored in the whatever receiving the key input. So it means that uh, when you press caps lock, then when you press A, you'll get one scan code. When you press caps lock, you'll get some other scan code, and when you press A, you'll get some other scan code. The scan code of A, capital A and small a will be same. So how do you differentiate between a capital A and a small a smaller case and lowercase and uppercase letter? That thing you have to store. You have to store the information that a caps lock was pressed before, and until the caps lock is pressed again, whatever that you read, you should be taking that as uppercase letters. Same way shift, and also num lock, everything. So that's complex protocol. You can see this is a complex protocol for caps lock, for shift and also tab as special characters, but you can simply program for smaller case alphabets and numbers. That's it. It should be sufficient. No need to even do the arrows and other functional keys. So you can use this thing. This again, the second link where scan code. We have scan code decoder also. So if the input is this is scan code and this is ASCII. You try to use these files and this thing and try to achieve whatever the key the lighting. And once you get the data, and this runs separately. So how do you read an input? So the goal that you should have is that the keyboard reading will happen automatically. So until you press suppose you press A, then let's assume that whatever value that you read is stored to a register. So when I press A, the ASCII code, you convert the scan code to ASCII code and then store it in that particular register, 8-bit register. And when I press S again, if I press S, that 8-bit register will change to this ASCII code of S, something like that. But how do I know a double press A? Like if I press A and then again press A, how do you know that? So what you can do is that you can have a 8-bit. So again, was a design choice. Like this is how engineering problem where how do you detect that? So what we did is that there are two things. One is an 8-bit register and one is a 1-bit counter 01, and then 8-bit register. So every time I read a value, let's say I read a value A, that ASCII code will get stored in this 8-bit register, and that particular counter will be set to 1. That's what you should do. Now it's the job of the processor to keep on looking at this counter. If it is 1, then it has to take that 8-bit value, ASCII value, and then store it in some buffer. And it should set this counter to 0 again. And the next time, the keyboard will again write that 8-bit register and set that to 1. The job of the keyboard module, the system integration part of that is that you will be continuously writing whatever ASCII value that you read to that particular 8-bit register and then set that counter to 1. That's your job. And the opposite side, like this 01 can be like understood as a interrupt. And the processor in every fetch cycle, like how do you detect an interrupt? In what interval? So what we did is that at every fetch cycle, the processor will see whether there is any interrupt, maybe a timer interrupt or keyboard interrupt. If there is any of these kinds of interrupts, then it will not execute the instruction. Instead, it will directly jump to the interrupt handler. So in every fetch stage of every instruction, it will check whether there is any interrupt. Only if there is no interrupt, only then it will go to execution. So interrupt is having higher priority. So as soon as an interrupt comes, the processor, the fetch cycle will jump to the interrupt location. So fetch and fetch. So you'll have two fetches. In this fetch, you'll detect the interrupt, and in the next fetch, you'll go fetching the instruction of the interrupt handler. So this is how you do the keyboard, and how to read this keyboard. You assign a special memory address which is accessible. So when the user asks for this particular memory location, you assign this memory address to be something out of the memory address, total address. The address is 240 KB, right? You assign something out of the scope, or you assign a specific address for this particular 8-bit register. Whenever the address fetching, when you keep checking, like you have to, like we divide the memory to 3 parts, right? So whenever the user asks for this particular address, you will be checking whether it's a display memory address or a ROM address or RAM address. You'll be concatenating everything based on the number if it is more than 9600, because the memory has 9600 bytes. 9600 bytes or words, I don't remember. If the address is more than that, and if it is less than the ROM size, then we are addressing the ROM. If it is more than that, we are addressing the RAM. Even if it is this for a particular value, out of scope value, then we are addressing keyboard, one particular value. It is basically a if else condition, something like that. You will be you'll be seeing this address and then read that. Again, how to flip that interrupt counter? We'll be finding some uh, difficulties in doing that, because you cannot directly flip a counter and from two different ways. You have to do that somehow. You'll be able to find that. You'll be able to solve those challenges. So this is how keyboard and display are connected to the main processor. So this we have come to the final slide of the introductory presentation. Okay. One thing that I get like I like plan ahead before any project is that or something called a goal. What is your goal on for the project? Before any project, you should have some goal, like what is that you are going to achieve at the end of the project. So our goal was to be able to play the game Galaga on our computer. If you know, Galaga is uh, it's a simple game, a retro game. Retro, this can find in old game controllers. So what happens is that from there will be a shooter at bottom, and you have to shoot asteroids falling from sky. There will be different. This is something a complex version, complex animations. We like our goal was a simple asteroids. Some letters will fall maybe, or some hash. Like some asteroids will fall from sky from top, and there'll be shooter and which has to escape those asteroids. So it's a survival game, and also when you shoot a asteroid, you get some points, highest score, highest survival time, something like that. That was the goal when we started the project. But like we didn't achieve the goal, uh, mostly because of the complexity of the game, programming that game itself. But we built a computer. Maybe if we had a week more time, maybe we could have built that game. So we partially, or like we were we were in a position to achieve our goal. uh, we can say that we have achieved our goal also, because we at the last moment we went to some simpler game, a snake game, which I think if you see the programming would be very easy. Both of them, you need a random number generator that randomly uh, throws asteroids based on the difficulty. Like if the time is zero, then the number of asteroids will be inversely proportional to the time survived. And you shooting, and you will have a bullet. So if you keep on shooting, you'll have a bullet, and each time the bullet will go one step up, and the asteroid will come one step down. And if the location of the spaceship and the asteroid is same, then you lost the game. The goal is simple, but I don't know. But we settled for a snake game at last. But again, we can say that the goal would have been achievable. We would have achieved that goal, even if we tried, like 2 3 more, even 1 week. 1 week should be enough. Uh, that was our goal. So I just suggest that you also should have some goal. Like what is that you're finally going to achieve? Like what is that going to run with the final computer? What is that you're going to show in the final presentation? That should be your goal. Like once you saw this video, right, you will have an understanding like how is the presentation going to happen. And uh, and since you have the understanding of our project, you should be able to complete whatever we did by checkpoint 3, which is 1 month before the final presentation. So when we did our project, we got the display working, we got the processor working uh, without the interrupts uh, by checkpoint 3, because we the keyboard and the keyboard, basically keyboard only. Once we have keyboard, then we could have moved to the process scheduling. Without keyboard, like process scheduling is something additional, right? The basic one is keyboard. So we did display and processor. Both were working by checkpoint 3. Our checkpoint 3 presentation was we displayed Fibonacci numbers on the display. 1, 1, 2. It continuously displays Fibonacci numbers and then repeats again. That was our like when we tested, we displayed Fibonacci numbers on the LEDs. Once we got the display working, we displayed it on the actual numbers. 1, 1, 2. You'll see the numbers in the just like you saw in the the final our presentation video. Like just like that, we displayed 1, 1. There is no interaction. The only program that runs is that displays Fibonacci numbers. That was our completion for by checkpoint 3. Since you have the understanding of our project and all these material and also this video, these 3 videos, you should be able to complete whatever we did, both display working, keyboard and processor working by checkpoint 3. Once you did that, you'll have 1 month of time to do the additional. That's what we did. So again, in addition to what our the computer like that was asked like the goal of the from sir's perspective. Additionally, we did process switching and scheduling. What you can do is the UDP stack. If you see this FPGA for fun, they have the entire Ethernet protocol explained. What is it? They explain the entire Ethernet protocol. They give you code, and you can actually send messages from your Jaiba board to your computer. You can send messages and receive messages. We thought of building a UDP stack. We had a CN lab along with that. You already completed your CN lab, but we had CN lab and CST lab side by side. Our CN lab got postponed by 1 semester. We did a UDP stack in we built UDP stack in Nachos project. So the entire project of our CN lab was to build a UDP stack from top to bottom, all the 7 layers, all the 4 layers. We used the internet protocol, all the 4 layers from scratch in Nachos project. But so we had an idea how to build a UDP stack. So we thought maybe in our language we could build again a UDP stack using these Ethernet connections from this thing. But we didn't have enough time. But we had I had the complete idea of what to do. Maybe for 2 more weeks, if we would have been able to communicate between 2 Zybo boards, like a chat system. I enter one message, they enter one message, like a chatting using 2 computers. So you can do that. So UDP stack, you can aim for doing UDP stack, something new in this year. Likewise, if we do, like, it keeps on, the complexity increases, and then it will become benchmarks for later projects, later batches. And programmability. If you see, all the programs that I ran in the presentation which were written previously into the hardcoded into the OS and then run there. So I'm just using a computer. It's like a pre-compute, like a game. Like if you see the handheld games, like you cannot install maybe something where you cannot install new games or feature phones. You cannot install new apps. You cannot install new anything. The only thing is it comes with some predefined installed software, a one game, a snake game or something. The old phones, like nowadays feature phones, button phones. You can only use that. You cannot install new apps. You cannot do anything other than what it is given. That's what our computer is right now. What you can add is that programmability. You can write a editor which will enable the user to write code, and then whatever we build, the entire front end, like the front end like compiler, assembler, translator, virtual machine, everything, high level language design, you can design a separate high level language, something different from or same also, no problem. I think so. In that case, you will be having 2 languages. one language runs in the computer and one language will use it to program the computer. So you will build the compiler, translator, assembler in the CNP language. Like we use CNP language, right? You will have your own language. You will be building all these three components. You would have used C++ or Java till now. You should have made your job of writing these three components easier. But now you will be writing all these three components in your own language, whatever you design. So it's a even more hectic and also much higher level task, because you should build such a language and you should have such a compiler such that that language and that compiler are capable of compiling a compiler. You understood, right? You will be writing a compiler in your own language, which means that your language should have such a construct, such strong and powerful constructs, which will enable you to write an assembler, compiler, and a translator. That's a very difficult task. So at this point, you can use virtual system to make a virtual machine to make your task easier, which means you will be building only a virtual machine and a compiler. You don't have to use assembler. You really understand, like when you go to the course, you'll understand all this. You can build your language to be that powerful and also compiler to be that powerful. The library, you should build a big library, a powerful library beforehand. Using all these things, you'll be designing a compiler, maybe for the same language or for some other language, for a simpler language, and then write a virtual machine for that language, which means that you can write your program from the start. Like you can just boot the OS, you'll write, let me write an Fibonacci program. You write from start. There is no hard-coded Fibonacci program already loaded with the OS. You'll be programming a new Fibonacci program. You'll write Fibonacci program in the second language that you created, which can be the same as the first language, in the second language that you created, and then you'll be compiling with the compiler that you have written in your first language, which is already loaded with the OS. So at least that should be loaded with the OS. So you will not be loading every program, but you will be loading the compiler and virtual machine along with the OS into the system. And you will use that compiler to compile your new Fibonacci program. And then you will use the virtual machine to run your Fibonacci program. The use of virtual machine is that you don't have to convert that particular thing. You can convert also, but no problem. But because if the languages are different, then you can use a virtual machine, because it is easy to use a virtual machine than to build a translator and assembler. So you will run that 3 code in your virtual machine that you built in your own language and then execute it. That way, you will have a very nice programmability. That is twice the task of what you did. Like at least more than that would increase your task load by at least 40%, 40, 30%, 30, 40% programmability. If you had from start designed a very good compiler and language, then it should be easy. Again, 30, 40%. And again, pipeline processor, at least with hazards. So pipeline processor is a must. Like that's what sir told. Like our seniors did a single cycle processor, we did multi-cycle, and this time it would be pipeline processor. You have to compulsorily build a pipeline processor. You must do this. You can do this. You must do this. You may not like do all those hazard reduction, like forwarding, data forwarding, and branch prediction. You should be able to do that, but even if you are unable to, just a stalling mechanism, if you can include in the processor, that should also be enough. That is also a much bigger leap from what we did, like for your project. And cache also, you can use cache memory and stage memory access. Like the only reason when I told when we reduce the clock, when we increase the clock frequency, the addresses are not settling. The main thing which occupies the highest time period is the memory stage. Accessing the memory to 40 KB took very long time. That's what is the bottleneck there. What you can do is that you can divide the memory stage into two parts, because you are doing it doesn't make sense for us to divide the memory stage into two parts, because it's not pipeline. If you divide it to two parts or in one part, it's going to take the same amount of time to execute all the instructions, the runtime instruction. But since you're doing a pipeline processor, it would be beneficial for you to divide that memory stage into two parts. So mem1 stage and mem2 stage. Maybe mem1 stage and mem2 stage. So by the end of mem2 stage, you'll be able to get the required value. If you do two memory stages, then you should have cache basically. So in the first memory stage, you'll search the cache, and if it is a hit, then you'll be directly, it'll right away go. Or if it is a miss, you'll go to second memory, the bigger memory, and then you'll access that. Or what you can do is that you can directly put a request, or you can directly put a request at the start of the first mem stage, both for cache and the complete memory. If you had to hit in the cache, you'll continue that right away. If you don't hit in the cache, but it's not a hit, if it is a miss, then you would have 2 memory clock cycles for you to fetch from the RAM. In which case you would get the required result at the end of second stage. So we can use this. It's an additional power consumption because you will be doing both cache search and the memory search, RAM search, but it's speed up. The benefit is speed up. You can do many of like these things. You can include cache, you can stage memory access, all these things. This is what I planned when we did the project. Like we planned. Now that's what this I remember right now. But you can have your own ideas. To do everything, you should be able. If you want to do all this, then it is mandatory for you to complete the Go game. Whatever we did, at least in the display, keyboard, processor to be working with at least some programs running by checkpoint 3. Only if you are good, then you can add all this in the last 1 month. So the project is for 4 months. In the first 3 months, you can, with the help of all these videos and this and the explanation, you can do it whatever we did by checkpoint 3, and then in the last 1 month you can add these special things like additionally whatever we did. I think most of our work was done after checkpoint 3 only. We had only 20 days, 20 or 15 days only, because people kept on postponing, like nothing is there to show. So they kept on postponing checkpoint 2. Actually, there was a 1 month, one month gap, like it's what's our plan, but it kept on postponing, like checkpoint 2 got postponed. So there should be at least some time between checkpoint 2 and checkpoint 3. So checkpoint 3 got postponed. And then at last, there was only 15 days gap between checkpoint 3 and final presentation. So don't do that. Try to complete, regardless of what checkpoint is, try to complete whatever we did before 1 month of your final presentation, and then the final 1 month add these additional things. Okay, so that's the end of the introductory video. This is what I plan. I plan for much elaborate videos for each component, but I think I spoke very much on each topic. That making a other video would be same like this. So I think by this time it would have more than 3 hours, 3.5 hours of video. It should be, it's so much, you'll get sick of it. So thank you for watching this. If you had come at this point, then you would have, I'm hoping that you have watched all the 3 videos. Thank you, and hoping to see good projects that much bigger than what we did. So thank you. And also I'll thank Dr. Jainaran for this project also. And one thing I would say is that this project is going to be the biggest project that you would have done in your entire BTech. Even when compared to BTP, BTP would also be something small. Like even more than BTP, this project would be like, if you do it completely, it is 16 number project. Just because it's 16, the individual contribution may be small, but in the entirety, it's a 16-member project for 1 semester. So it's going to be the biggest project that you would have. You'd be remembering this project if you do it correctly. If you at last, if you could achieve the display, keyboard, and processor to be working, and then if you were able to run few programs, then that's a very big achievement, and you'll remember that. So try to enjoy the project very much. It's going to be very difficult, at least because of not because of that, because of the many people to manage, and also newer things, the process design, and there are even for you compiler design, everything are much new. And also placement season is going on. You may not find everyone at every time to do the project. Will be going on. So and also you'll have other courses also, and also BTP first phase. So there are many things that will be going on, but you should be able to, like you will be able to, like we were able to. So you must be able to complete that. Thank you.